electrostatics. Like we had on one side Coulomb's law, then we brought Gauss law. No? What is the advantage of like Gauss law? Finding out the electric field due to different charges systems is much easier with the help of Gauss law, and moreover for conductors inside the conductor. So what is the field due to conductors? Electric field. I think the Gauss law helped us a lot. No? Similarly, now here Biot-Savart law. Biot-Savart law. And we have here Ampere's circuit law. So what is the role here? The point charge, here the current element. So now how the Gauss law was helped us to find out the field due to charged conductors. Similarly here, if a current carrying sheet, a current flows in a cylinder, then how to get the magnetic field? The Biot-Savart law will not help us. It's having its own limitations. Means if a current flows in a wire of radius A, you say that one, where current is flowing along the wire, because the current will flow through a wire, no? This one. So from Biot-Savart law, we are able to predict the field. We are able to predict the field outside somewhere here. Yes, for R greater than A only, we are able to predict the field, no? And this is a long wire. And what is the formula? B equal to mu naught I by 2 pi R. What about the field inside? Will there be any field? Is what the question will arise. Yes, there will be field inside also. So how do we can determine that particular field inside? So Biot-Savart law will not help us, because strict condition for R must be greater than A, that one. Even equal to A also, we can't do that one. So this is what happened here, no? In all our problems. We never went inside the current carrying wire. It was only external to the wire. Now with the help of Ampere's circuit law, we can easily find out the field inside the current carrying conductor. This is our aim. So for that, what happens? First, we will bring that law. Then we should learn how to use that law. Then we'll go for applications. This is a background here. So definitely in exams, you must, whenever you get a problem, check first, can you apply Ampere's circuit law? So that you'll get answer very easily. Then if even Ampere's circuit law is not possible, then go back to the Biot-Savart law. So the law itself is checked. Similar to like a Gauss law, no? How we started, like there the Gaussian surface, then the net charge enclosed, we define few terms, no? The same approach is what we are going to develop here. So let me put that law, the line integral. The line integral of magnetic field over a closed loop is equal to mu naught I, mu naught times the total current crossing the area bounded by the closed curve. By the closed curve. Provided the electric field inside the loop remains constant. This is the last, that is later, this part you avoid time being. When we discuss EMI chapter, no, then this you'll get that one. Why the field should remain constant, so that what I shared highlighted, no, don't bother about that one. Let's focus only on this particular basic law. the first, the highlighted one, try to avoid that one. At this particular stage, not needed. Okay, this is about the statement is what we have brought it. The line integral of magnetic field over a closed loop. So what is it, the total? Equal to mu naught times of I. Like there we had like a E bar dot ds equal to q in by epsilon naught. What is q in? Net charge enclosed. What is I? The current enclosed by the path. There, what is ds? Gaussian surface. No, this was used to help us Gaussian surface. Similarly here, the dl bar, it will help us to predict the path, closed path. Closed path. Is it okay? So I think there's a difference between if I write. Okay, let's focus on what do you mean by that integration in closed path. Suppose that there's a loop. Let this be dl. So if I integrate, so length of the loop, side length of the square loop, it is dl. So integral of dl, this should be equal to how much? 4l. I'm going to integrate in a closed path. Then integral of dl bar should be 0, no? I think you be careful. Same thing if I write it, integral of dl bar, it should be 0. Integration in closed, vector sum of all that resultant should be 0, no? The net displacement will become 0. Just only integration in closed path will be 4l. Now it can be of different shape, loops will come. So now we may get so now the closed path, let me take dl. Then what is the integral of this one? So let r be the radius of this loop, 2 pi r. Okay, integration, if you add up all such elements, what you get? You'll get the perimeter of that loop. That's the meaning, integration in closed path. So that's what in magnetic field, the line integral of magnetic field or a closed loop, because of closed loop, no, therefore we are putting circle, that one. So that's the meaning. Okay, we know what is this B. What is a B? B is some sort of magnetic field. And what about I? Current enclosed by the plane curve. So let me introduce. So this is the curve. Curve, let me take it red color one, this one, and let this be the current carrying wire. Let I be the current. Then what is DL? DL is this one, not a surface. It's a curve. You can see that one. I'm just putting random shape. It can be of anything. There's nothing that it should be square or anything, that one. So we know that there's a long wire. Time being, so let's focus on the long wire here. So there's a long wire. So then what is a B bar? B bar is what I'm defining at this particular point. And this is the DL. So what is telling, integral of B bar dot DL is equal to mu naught times of the I. What is I? I is the current enclosed. So then I can integrate in clockwise or anti-clockwise. No, if you integrate in the direction of B bar, then that current should be taken as positive. If you integrate opposite to B bar button, then the current will be taken as the negative. So when I will be positive or negative, now due to this current I, in what direction we can expect B bar? Somewhere like this, tangential everywhere here. So some rough diagram need not be tangential because they're not a circle. So it'll be like this. No? Then DL, there'll be angle between them also. So B bar dot DL cos theta. So like that at different points, what will happen to value of B bar will be different. DL will be same, and angle between B bar DL will be different. Equal to mu naught plus I, right? Why I? You can see from the diagram. Here the same path. So this is what the current here is. I'll show like this. This is side view, and this is a top view. You're viewing from top. Then at various points, let's go for here. So here B bar, P bar, B1 will be like this. And this is the current element. So there is an angle between them, no? There's some angle, how much? Theta 1. Now again at this particular point, you look at B bar and the current element. Both will be in same direction. So look at this particular point. There's a current element. And there's no rule that B bar should be parallel to DL bar at all points. At some points it may, or and look at this, at this particular point. One more outside will take it. B3 and this is DL bar. So look at that, there's some angle, no, between them. So what is the expansion of this? The left hand side term will be integral of B1 DL cos theta 1, B2 DL cos theta 2, B3 DL cos theta 3, and so on, is equal to mu naught I. When you can take I positive, so we know roughly the B bar here, how it will produce the field everywhere. If I concentric circles, and if I draw a tangent, this will be like this, no? So if I integrate in the direction of B bar, then that particular current should be taken as positive. Current enclosed by the path. Current means not one dot, long wire. Strictly, what is the condition for this? This should be a long wire. Not semi-infinite wire also. Strictly, it should be a long wire here. And don't say current enclosed by a long wire. Just you say current I. Here I means it's a long wire only. If it is semi-infinite or some finite, we'll see later on. So net current enclosed by the closed path. So this should be the plus I, we should take it. Now we'll take the next condition. If there's a closed path, let me take closed path circle itself. So there are two current carrying elements are there. One is I1, and there is I2. Now it's left to you. I'm going to take integration in anti-clockwise. So there's a direction of DL, I'm taking it. Then which current you should take positive? So which particular long wire will produce the B bar in the direction of DL? So integration in closed path, some books they're shown arrow, I'm trying to avoid. I'm just showing DL bar something. So I'm going to integrate in anti-clockwise. So which current can produce B bar in the direction of DL? I2. So therefore I2 will be positive, I1 will be negative. So then what is the formula? B bar dot DL. What is this? This is a curve. Like how we had Gaussian surface, no, it's a curve. So this should be equal to mu naught I2 minus I1, or we'll take this I1 minus I2. Okay, there's a meaning of this. Of course, can we simplify LHS? Okay, timing, let's wait here. So there's a basic overall, the meaning of that net current enclosed by the path. So when it should be I1 should be positive or negative, it all how you integrate. Then this one. So let's now go for that plane curve. What is that? Or say that curve? What actually meaning of that? What actually the meaning of that? So we'll explore now that particular law itself, the various terms in the law. So first I'll begin with the what is the value of?
Sir, can you scroll up once?
Okay.
Yes, sir. Over, sir.
Let's take the there's a plane curve I'm taking. This one. So let there be a current carrying wire here. So current, let it be, so here out of the plane. Let me show like this. There's a long wire. And what is the meaning of that mu naught I? So like a, for any shape, now I'm going to put like this. There's a plane curve. Here also this will enclose a current I. So what is the value of B bar dot DL for both the loops? There's a loop. You can call it as a loop. It's a square circular loop, no? And what is this? Square loop. So what is the value of B bar dot DL? What do you mean by B bar dot DL? There's a product, no? That not B bar dot S. B bar dot S will be zero. It's a Gauss law for magnetism. Ampere circuit law is B bar dot DL bar, that one. So I'll say both is same, mu naught I. But sir, like a loop, here you brought circular loop, here square loop. And the value of B bar dot DL for both square and circular loop, I say it is equal to mu naught I only. Value of B bar dot DL bar for circular loop. How much? Mu naught I. Value of B bar dot DL for square loop. Mu naught I. This looks little bit funny, no? There's, sir, what is the reason? How you are writing this particular thing? So we'll do one thing. Just we'll deform this loop. We'll deform this loop. And I'm going to deform it. Okay, this is the some notch I produced. All of you, notch. Okay, this one. And the loop, it has taken shape like this. The same current carrying wire is present. So here, the same current carrying wire, long wire. So I'll produce a notch. Let R be the radius, what we earlier assumed. And let this be delta R. So let this notch subtend an angle delta theta. So let this length of the arc be ds. So here let's calculate the field. Field here how much it will be? B1 bar. And what about field? Field here will be B2 bar. Let me go for this one. So value of this one. So what is the arc length? So B bar dot DL, no? So everywhere the B bar is parallel. We know it's a long wire. Due to long wire, how the lines of force will be? Concentric circles. So everywhere at all points on this circle of radius are, how B1 bar will be? Parallel to the length parallel to the length. So what is the angle between B1 and DL? At everywhere it will be parallel, angle is 0. So I can directly write. So what is the value here? It will be, so directly B1 into, what is arc length? So this will be 2 pi minus delta theta r plus B2 into notch. This is the notch. Will give some name. I deformed it. So what is the arc length of the notch? Let it be ds. So this I will expand this one. So b into 2 pi r minus b into delta theta r, or one more step I'll write it. What is delta s? R plus delta r into delta theta, no? Now let's come for what is the magnitude of magnetic field? Mu naught I 2 pi r. What is magnitude of magnetic field at this particular point? Because this is r, no? R plus delta r it is. So this pi will not be there. Oh, sorry, long wire, no? Not ring. Yeah, 2 pi r delta r. So let's simplify this. So mu naught I 2r 2 pi r minus mu naught I delta theta r 2 pi r mu naught I r plus r, that cancels. So therefore this will be r plus delta r, numerator denominator get cancelled. So mu naught delta theta by 2 pi r. This r will not be there, no? So finally, how much we are getting? 2 pi. Look at all the calculations. So I ended up this much only, no? So even if I make it, I deform the loop, then what is the value of b bar dot dl in closed path? Mu naught I. Let's go back to this one. What is the value of b bar dot dl for this? I'll assume here length dl. The value is how much? Let it be b1. So then what we write? b1 dot dl equal to mu naught I. This will be b dl cos 0 at all points. And what is the net current enclosed by the loop? I. And why current I should take positive? Because I'm integrating along the path in which the field is there. The field is directed. So this B is constant at all points. I'll take outside. So dl mu naught I. This is there. Now what is integration in closed path? 2 pi r. So look at the value. This loop, what is the b bar dot dl? b1 bar dot dl. We ended up equal to mu naught I. And even in this loop also, though I deformed it, how much we ended up? Equal to mu naught I. So therefore, shall we put one condition? So whenever you are calculating b bar dot dl, in closed path, is it the shape of the loop matters? Can you hear me?
Yes, sir.
The power gone. With mobile will run the show. No, look at this one. So what is the value? So I made a some notch. I deformed the loop. Earlier it was a closed loop, a circular loop. Now I deformed. Then also what is the value of b bar dot dl for the closed path? Mu naught I. So therefore now shall we put any condition that the value of b bar dot dl is independent of shape of the loop? All of you, are you getting now? So here shall we put like the value of integral of the magnet field along a closed path and some current carrying wire is independent of shape of the path or shape of the loop. So one strong or so like a bold statement I'm putting. So you need not to bother now the shape of the loop. So whichever shape you want, you can assume it. It's left to you. You have got full freedom to assume. So first statement I'm putting, these statements are what? Very important for us. The value of line integral of the magnetic field along a closed path encircling a current carrying wire is independent of the shape of the path. The shape is telling. So is it justified now? Once again, so what is the value of b bar dot if the path is circle? Once again, so here the path is circle. There's a loop. Then other student what happen? He will draw the loop like this. He will deform it. Then what is the current enclosed? Let it be I. It's a long wire again, not some current element. Long wire. Then what is the value of b bar dot dl for both? For both the loops, loop 1, loop 2, it is same. So what is the net current enclosed by both the loops? Current element. What value of b bar? Once again, I'm putting value of b bar dot dl for both loops is mu naught I. Okay, got this one now. So is it what is that shape of the loop? It's your convenient. It's left to you. Is it a real or imaginary one? Next question comes. I'll put all the conditions one by one. Okay, this is about. So now let's take another. Try to add a pages.
Sir, can you scroll up one, sir?